A dark world drifts forever through the endless night. This is a rogue planet, an entire world untethered from the light of any sun, sailing the cosmic ocean alone. By the end of this journey, you will understand 25 of the deepest mysteries surrounding these nomadic worlds, mysteries that could rewrite our place in the universe. We will confront the possibility of life in absolute darkness and grapple with the chance that one could someday visit our own solar neighborhood. What does it mean for a planet to truly be alone? The first and most fundamental mystery is how a planet finds itself utterly alone. The journey into darkness begins with a violent birth. In a young star system, planets are not polite neighbors keeping to their orbits. They are massive, newborn worlds jostling for position in a crowded disk of gas and dust. Gravitational tugs of war are constant. When two giant planets pass too close, one can be catapulted outward by the other's gravity, a cosmic slingshot that sends it careening past the system's edge and into the interstellar void forever. This is not a gentle push, but a catastrophic ejection, a world torn from its sun in a moment of celestial chaos. But there is another, more solitary origin story. Some rogue planets may never have known a star's warmth at all. They could form in isolation from the direct collapse of a small, dense pocket within a vast interstellar cloud. Picture a knot of gas and dust too small to ignite as a star, yet massive enough to collapse under its own gravity, coalescing into a solitary world adrift from the very beginning. This process blurs the line between a planet and a failed star, a brown dwarf. Recent computer simulations paint a startling picture of our galaxy's violent youth, suggesting these ejections were far more common in the early universe when star systems were denser and more unstable. The cosmos may be littered with the orphans of these ancient gravitational battles. This leads directly to our second great mystery. Are most rogue planets lonely giants, colossal worlds of gas and ice, or is that simply all we can see? Our current methods of finding these dark wanderers are heavily biased toward the largest and most massive. The primary technique is called gravitational microlensing. It works like this. When a rogue planet drifts in front of a distant background star, its gravity acts as a temporary lens, bending and magnifying the star's light for a brief period, often just hours or days. A more massive planet creates a stronger, more detectable lensing effect. A small, rocky world like Earth would cause a signal so faint it would be nearly impossible to pick out from the noise of the cosmos. So our census of rogue planets is like searching a dark forest with a flashlight that only illuminates the bears, completely missing the foxes, rabbits, and mice. This detection bias forces a profound question. Does the prevalence of Jupiter-sized rogue candidates, like the intriguing object CFBD SIR 21490403, mean gas giants are more commonly flung from their systems? It is a compelling idea. In the gravitational chaos of a young system, the most massive planets have the greatest influence, but they also become the most likely targets for violent interactions. They are the bullies who often get thrown out of the celestial schoolyard. Or is the simpler answer that these giant worlds, still warm from their formation, simply glow more brightly in the infrared, making them stand out against the cold backdrop of space? The truth likely blends both. The giants are both more frequently ejected and easier for our limited senses to perceive. This means a hidden population of smaller, Earth-sized rogue planets could vastly outnumber the giants, a silent multitude of dark marbles adrift in the galactic dark, completely invisible to our current searches. This profound invisibility forces us to confront an even more compelling question. If countless dark, Earth-sized worlds are drifting unseen, could any of them be alive? The idea seems to defy every rule we know. Life requires energy, and a planet without a sun is a frozen tomb, its surface plunged into temperatures near absolute zero. A star provides the steady, radiant warmth that drives photosynthesis, weather, and the chemical cycles that make a world habitable. Strip that away, and you are left with what appears to be a permanent global ice age. Surface life as we understand it is simply not an option, but life on Earth has repeatedly shown us that it is far more ingenious and resilient than we ever anticipated. It thrives in places we once considered utterly lifeless. The real potential for life on a rogue planet does not lie on its frozen, airless surface, but deep within it. Imagine a rocky rogue world, perhaps one ejected early in its solar system's history while it was still geologically active. Radioactive elements in its core, like uranium and thorium, continue to decay, generating heat that slowly leaks outward. This internal warmth could be enough to maintain a vast global ocean of liquid water trapped beneath a thick, insulating shell of ice. This is not science fiction. We see this very architecture at work in our own solar system on moons like Jupiter's Europa and Saturn's Enceladus. They are frozen on the outside but internally heated by the gravitational tug of war with their giant planet, which flexes their interiors and generates friction. A rogue planet could experience similar tidal heating if it managed to hold onto a moon during its violent ejection. The gravitational dance between the planet and its moon would continuously churn the interior, providing a steady, geothermal energy source that could last for billions of years. So picture this dark wanderer. Its surface is a barren, cratered landscape of eternal night, scoured by cosmic rays, but descend through miles of ice and you might find a warm, pitch-black ocean, perhaps dozens of miles deep under immense pressure. In that abyss, the chemistry for life could be brewing. On Earth, entire ecosystems flourish completely independent of sunlight around hydrothermal vents on the ocean floor. Bacteria there use chemicals like hydrogen sulfide for energy in a process called chemosynthesis. Giant tube worms, blind shrimp, and strange crabs thrive in this perpetual darkness, powered by the Earth's internal heat. A rogue planet's subsurface ocean could host similar vents fueled by its own geological activity. The building blocks of life, organic molecules, are common throughout the galaxy, and they would have been present when the planet formed. In that dark, warm, mineral-rich water, the leap from chemistry to biology might just be possible. This leads to a staggering possibility. If rogue planets are as numerous as some astronomers suspect, these dark, ocean-bearing worlds could outnumber all the traditional, star-lit planets in the Milky Way. The most common abode for life in our galaxy might not be an Earth-like world orbiting a sun, but a lonely, ice-shrouded globe drifting silently through the interstellar void, its biosphere hidden forever from the light of any star. This possibility of hidden oceans forces us to ask a truly galactic question. Just how many of these dark wanderers are out there? The answer, based on the best data we have, is almost incomprehensible. Current estimates from gravitational microlensing surveys suggest there could be billions, perhaps even trillions, of rogue planets sailing through the Milky Way alone. Some astronomers argue these lonely worlds could outnumber all the planets that orbit stars, making them the most common type of planetary body in our galaxy. Think about that for a moment. For every Earth, every Jupiter, every world circling a sun you see in the night sky, there could be another dark counterpart drifting unseen in the space between. The primary evidence for this invisible population comes from dedicated sky surveys with names like OGLE, the Optical Gravitational Lensing Experiment, and MOA, Microlensing Observations in Astrophysics. These projects don't look for planets directly. Instead, they monitor hundreds of millions of stars at the crowded center of our galaxy, watching for the telltale flicker that occurs when an unseen object's gravity magnifies a star's light. It is a statistical fishing expedition. By counting these rare microlensing events and analyzing their signatures, scientists can extrapolate how many unseen massive objects, including rogue planets, must be drifting through the galactic lanes to produce the number of flickers they see. The math points to an ocean of dark worlds, but getting a precise census is one of astronomy's greatest challenges. Each detection is a fleeting, one-time event. We see the planet's shadow, but then it is gone forever, its path untraceable. We cannot point a telescope at it again to confirm its size or composition. Furthermore, these surveys are most sensitive to rogue planets roughly the mass of Jupiter, orbiting at a certain distance from the galactic center. They are essentially taking a small, blurry snapshot of a single neighborhood and trying to estimate the population of an entire continent. The smaller, Earth-sized rogues, which might be far more numerous, remain almost entirely hidden from this technique, so the number we talk about, billions or trillions, is not a head count. It is a profound estimate, a shadow on the wall of a cave, hinting at the true scale of what we cannot see. It suggests our galaxy is not primarily a collection of well-ordered solar systems, but rather a vast three-dimensional swarm where dark, nomadic worlds are the rule, not the exception. This invisible majority quietly reshapes our understanding of what a galaxy is made of. The sheer number of these dark worlds points to a history written in celestial violence, a history that may stretch back to the very dawn of time. This brings us to a mystery that reaches into the deepest past. When did the first planets go rogue? To find that answer, we must journey back to an era before our sun, before most of the stars we see today, to a universe only a few 100 million years old. This was a cosmos of extremes, smaller, denser, and far more chaotic. The first stars, known as population 3 stars, were behemoths, hundreds of times more massive than our sun. They burned with a ferocious blue-white intensity and lived fast, dying in spectacular supernova explosions after only a few million years. In the dense, swirling clouds of gas and dust around these titanic stars, the very first planets may have coalesced. But their neighborhoods were nothing like the relatively calm suburbia of our modern solar system. These primordial star systems would have been incredibly crowded and unstable, with massive protoplanets engaged in constant gravitational wrestling matches from the moment they formed. The death of their host star would have been an apocalyptic event. A supernova from such a massive star would have unleashed a tsunami of radiation and a shockwave of unimaginable power, likely stripping away any lingering atmospheres and violently perturbing the orbits of any surviving worlds. In this environment of titanic births and cataclysmic deaths, planetary ejections would not have been a rare accident but a common, expected outcome. Many of the very first planets to ever form in the universe could have become rogue within just a few million years of their creation, cast adrift into a young galaxy that was still assembling itself. Finding one of these ancient wanderers, a primordial rogue planet, would be like discovering a fossil from the cosmic dark ages. Its composition, untouched by billions of years of stellar recycling, would be a pristine time capsule. It would hold the chemical signature of that first generation of stars, telling us directly about the materials available for planet formation when the universe was in its infancy. Studying such an object could reveal the initial conditions for all the planetary systems that came after, providing the opening chapter to a story that ultimately led to us. But detecting something so ancient and cold, drifting in the vast dark for over 13 billion years, is a challenge that pushes our technology to its absolute limits, a search for a single, silent witness to the universe's first light. Finding these invisible worlds requires a trick of light itself, a cosmic illusion known as gravitational microlensing. It is a method that relies on one of Einstein's great insights, that massive objects warp the fabric of space-time around them. Think of space as a vast, taut rubber sheet. Place a heavy bowling ball on it and the sheet dips. Now roll a marble past the bowling ball. The marble's path will curve as it rolls through the dip, drawn slightly toward the heavier object. Light does the same thing. When a rogue planet drifts through space, its mass creates a similar, invisible dip in space-time. If this planet passes almost perfectly in front of a much more distant background star, the light from that star traveling toward us will pass through this warped region. The planet's gravity acts as a natural lens, bending and focusing that starlight, making the star appear temporarily brighter to our telescopes. This is the microlensing event, a fleeting brightening that can last from a few hours for a small planet to several days for a Jupiter-sized world. The key is the perfect chance alignment. The rogue planet, the distant star, and our telescope on Earth must all be in a nearly straight line. It is like trying to watch a specific streetlight in a city 1,000 miles away, and for a few days, a wine glass held at just the right angle in the foreground magnifies its glow. Astronomers don't see the planet at all. They see only the star's temporary brightening, a specific curve of light that rises and falls in a predictable pattern. By analyzing the precise shape and duration of that light curve, scientists can perform a kind of celestial forensics. They can deduce the mass of the invisible lensing object, the distance to it, and even infer whether it might have a moon as a secondary blip in the data. This work is a monumental exercise in patience and statistics. Projects like the Optical Gravitational Lensing Experiment, or OGLE, based in Chile, and the Microlensing Observations in Astrophysics, or MOA, collaboration in New Zealand, have been monitoring hundreds of millions of stars toward the dense star fields of the galactic bulge for decades. They take image after image, night after night, compiling a vast movie of the sky, searching for those rare, telltale flickers among the constant pinpricks of light. Every confirmed microlensing event is a triumph of international cooperation and long-term dedication, a single data point pulled from the darkness that whispers of an unseen world forever sailing away. While microlensing reveals shadows, another method searches for a faint, fading warmth in the endless dark. Young rogue planets, freshly cast from their stellar nurseries, still glow with the residual heat of their violent formation. For perhaps 100 million years, they radiate a dull, deep red warmth like a dying ember from a cosmic fire. This is the infrared glow, and it offers our only chance to directly see these worlds, not just infer their shadows. To capture this whisper of heat, we need eyes that can see the cold. Enter the James Webb Space Telescope, an instrument so sensitive it can detect the thermal signature of a bumblebee on the moon. By staring into regions like the Orion Nebula, a vast stellar nursery, Webb is not looking for the gravitational lensing of distant stars. It is looking directly for small, isolated sources of infrared light that are too faint and cool to be stars, yet too warm to be background galaxies. It finds them, these lonely points of warmth adrift in the colorful gas clouds. The images are breathtaking, rendered in false color to translate invisible infrared into visible splendor. A candidate rogue planet might appear as a deep magenta or a solitary crimson speck against the ethereal blue and gold clouds of Orion, a world captured in its stellar infancy, already set adrift. But here lies the subtle challenge of this hunt. That warm, reddish glow is almost identical to the signature of a very low-mass brown dwarf, a failed star that never gathered enough mass to ignite sustained fusion. The dividing line between a large rogue planet and a small brown dwarf is frustratingly blurry based on complex models of how they form. Is an object like those spotted in Orion a true planet ejected from a system, or is it a brown dwarf that formed alone like a star? For now, we often call them free-floating planetary mass objects, a careful name that admits our uncertainty. Each new infrared detection is a piece of a puzzle, helping us map the population of these warm, young wanderers and understand how many planets are cast out in the first turbulent chapters of a star system's life. They are the fresh exiles of the galaxy, their internal fires still burning, slowly cooling as they sail into an infinite winter. That faint glow from a young rogue planet hints at an inner warmth, but what if that heat source isn't just radioactive decay? The violent ejection that sends a planet into exile is a chaotic gravitational storm. In that turmoil, could a planet manage to hold onto its moons? This is the eighth mystery, the possibility of nomadic moons. When a planet is flung from its star, the forces involved are extreme and chaotic. Its moon system, if it has one, would be subjected to immense strain. A moon orbiting too close might be torn away by the star's gravity during the close pass that triggers the ejection. A moon orbiting too far, however, might simply be left behind, its bond to the planet severed as the world accelerates away. But there is a gravitational sweet spot. If a moon is in a stable, close orbit, the planet's grip could be strong enough to pull it along into the darkness, like a parent clutching a child in a raging current. Computer simulations suggest this is not only possible but perhaps even likely for some configurations. The survival of a moon transforms everything. That moon would no longer orbit a sunlit world but a dark one. Its primary source of light and warmth would vanish. Yet a new and potentially powerful heat source could ignite within the moon itself, tidal heating. This is the same process that keeps the subsurface oceans of Europa and Enceladus liquid. As the moon orbits its rogue planet, the planet's gravity pulls on it, flexing its interior. This constant stretching and squeezing generates friction, and friction creates heat. On a moon adrift in interstellar space, this internal warmth could be the only thing standing between it and absolute zero. A rogue planet with a large, icy moon could therefore become a far more promising habitat for life than the planet alone. The planet might be a frozen, geologically dead rock, but its moon, churned and warmed from within by their gravitational dance, could maintain a global subsurface ocean for billions of years. This ocean would be sealed under a thick crust of ice, protected from the vacuum of space and powered by the motion of the celestial dance. Now, picture the view from the surface of such a moon. The sky is not just dark, it is utterly black, devoid of any stars because its parent planet would fill so much of the sky. You would stand on a frozen plain, and hanging above you, dominating the heavens, would be a colossal, banded gas giant or a vast, rocky world. It would not be sunlit. It would be illuminated only by its own faint infrared glow, a deep, sullen red, and perhaps by the shimmering curtains of planet-wide aurorae, created as charged particles from space interact with any remaining magnetic field. This would be your only source of light, a permanent, majestic, and lonely celestial companion in an otherwise endless night. The existence of such binary exiles, a planet and its moon bound together in perpetual wandering, adds a profound layer of complexity and potential to the rogue planet narrative. It suggests that even in exile there can be companionship, and within that bond the possibility of a hidden, warm refuge. A world exiled into the dark does not have to remain as it was. Its journey is measured in billions of years across distances that dwarf the span of entire solar systems. During this epic voyage, it will inevitably pass through regions of space that are not entirely empty. It will drift through the sparse gas of the interstellar medium and through the denser, colder molecular clouds where new stars are born. This presents our ninth mystery. Could a rogue planet born from loss become a builder once more? Could it capture new moons or even a new atmosphere during its endless travels? The probabilities are incredibly low, but in a universe of infinite time and space, the improbable becomes inevitable. The primary challenge is speed. A rogue planet ejected from its star is moving fast, often at tens of kilometers per second. To capture a passing object like a free-floating asteroid or a comet, the planet's gravity must slow that object down enough to trap it in an orbit. In the emptiness of interstellar space, there are no other large bodies to help with this braking maneuver, no atmospheric drag to sap an object's speed. A direct two-body capture is nearly impossible. The object would simply swing past the planet on a hyperbolic curve and continue on its way, like a stone skimming past a planet's gravitational well. However, there is a theoretical pathway. If the rogue planet were to pass through a very dense region like the core of a giant molecular cloud, the environment changes. The space is filled with not just gas, but also countless small, icy bodies and planetesimals. In this crowded celestial traffic, a close encounter between three bodies becomes possible. Imagine a rogue planet passing by a binary pair of asteroids orbiting each other. The complex gravitational interaction could break the binary apart, flinging one asteroid away at high speed and leaving the other with just the right reduced velocity to be captured by the planet. It is a gravitational robbery, a cosmic game of billiards where the planet steals a new companion. The captured object would likely enter a wide, unstable orbit, but over eons it could settle into a permanent place as a moon. This would be a second-generation satellite, not born with the planet but adopted during its lonely exile. The implications are stirring. A rogue planet that managed this feat would no longer be a solitary wanderer. It would become a miniature, mobile solar system, a dark king with a captured court traveling the galaxy together. The presence of a moon, as we considered earlier, could provide tidal heating, potentially creating a habitable environment where none existed before. A planet that started as a barren rock could, through a chance encounter billions of years after its ejection, become a cradle for life. But what of an atmosphere? Could a planet stripped bare by its violent birth or a close stellar encounter gather a new shroud of gas? Again, the most plausible scenario involves a slow drift through a dense molecular cloud. These clouds are not a perfect vacuum. They contain vast reserves of hydrogen, helium, and trace gases. If a rogue planet moves slowly enough through such a cloud, its gravity could begin to pull the diffused gas toward it, accreting a thin, new atmosphere over millions of years. The process would be achingly slow, and the resulting atmosphere would be incredibly tenuous, nothing like the thick, swirling skies of Jupiter. It might be more akin to a vast, ultra-thin exosphere, barely detectable. Yet, for a world that had nothing, even this wispy shroud would be a transformation. It could provide a buffer against micrometeorite impacts, a medium for chemical reactions, and perhaps even a source of pressure to help maintain liquid water if internal heat were present. This paints a profoundly different portrait of a rogue planet. We must stop thinking of them as static, frozen relics cast adrift. They are dynamic, evolving worlds on journeys so long they defy human comprehension. A rogue planet could be a collector, a scavenger of the interstellar medium, slowly rebuilding itself atom by atom, encounter by encounter, as it sails through the galactic night. Its story is not one of an event that happened long ago, but of a process that is still unfolding. The surface of a rogue planet is a museum of eternal night. While its journey through the galaxy is one of dynamic change, its outermost shell could be frozen in a state of pristine preservation for billions of years. Without a star, the forces that reshape familiar worlds are absent. There is no solar wind to slowly erode the atmosphere, no ultraviolet radiation to drive complex chemistry in the skies, and no day-night cycle to create weathering through temperature swings. A rogue planet's surface exists in a profound and perfect deep freeze. Imagine a world where the very air has turned to snow. If the planet had an atmosphere rich in gases like nitrogen, oxygen, or methane when it was ejected, those gases would not simply vanish. As the world radiated its remaining heat into space, its temperature would plummet toward absolute zero. The atmosphere would condense layer by layer and precipitate out, creating a global frost that could be miles thick. The landscape would become a surreal, stratified cake of ices. You might walk, if you could, across plains of frozen nitrogen as smooth as glass, under which lie layers of solid oxygen and methane, all topped with a dusting of water ice as hard as steel. Craters from ancient impacts formed during the chaos of the early solar system would remain razor-sharp and untouched, their rifts and ejecta blankets perfectly defined, with no wind or rain to soften their edges over the eons. Mountain ranges would stand in silent, jagged relief against a sky devoid of any blue, only the permanent, glittering band of the Milky Way providing a ghostly backdrop. This is a fossil world, a snapshot of a moment in time perhaps 4 billion years ago, locked in ice. Yet this is only one possible portrait. For a rogue planet with a source of internal heat, the story of its surface is radically different. If radioactive decay or tidal heating from a moon warms its core, that energy must escape. It could do so through cryovolcanism. Instead of erupting molten rock, these volcanoes would spew a frigid slush of water, ammonia, and methane. Picture a vast, dark plain suddenly broken by a towering geyser of icy particles, erupting in slow motion under minimal gravity, arcing high into the black sky before falling back as a glittering, slow-motion snow. These plumes could create strange, overlapping flows of ice that look like frozen rivers, building up bizarre, lumpy domes and pancake-like features across the landscape. The surface would then be a battle between the deep cold of space trying to freeze everything solid and the internal warmth pushing to break through. It could be a fractured, ever-changing mosaic of ancient, preserved terrain and freshly erupted alien ice formations. Which version is more common, we simply do not know. Each rogue planet carries its own history written in ice and stone, a history we can only read from a distance by deciphering the faint whispers of light and shadow it sends our way. A magnetic field is a planet's invisible suit of armor, and for a world adrift, it could mean the difference between a dead rock and a living refuge. Our own Earth's protective shield is generated by a churning, liquid iron core, a dynamic engine powered by the heat left over from our planet's formation and sustained by radioactive decay. But a rogue planet cast into the cold faces a fundamental thermodynamic crisis. It is constantly losing heat to the frigid vacuum of space, without a star to warm it from the outside, and without the constant needing of tidal forces from a large moon, its internal fires will inevitably dwindle. The molten core will slowly solidify, and as it does, the planetary dynamo that creates a magnetic field will sputter and die. So the central question is not just whether a rogue planet has a magnetic field now, but whether it can maintain one for the billions of years necessary for life to possibly emerge in a hidden ocean. The answer hinges entirely on that internal heat source. A large, rocky rogue planet, similar in size to Earth or larger, would start with a tremendous reservoir of primordial heat and radioactive elements. Its core could potentially remain molten and active for many billions of years on its own. For a smaller world, however, the clock ticks much faster. It would cool more quickly, its core solidifying and its magnetic shield fading perhaps within a single billion years. This is where the presence of a moon becomes absolutely critical. Tidal heating from a gravitational companion does not just provide warmth for a subsurface ocean, it actively stirs the planet's interior. This sustained churning could keep the core liquid and dynamically active for an astonishingly long time, potentially far longer than Earth's own core will last. A rogue planet with a loyal moon could therefore be a magnetic wanderer carrying its own protective bubble through the galaxy. Why does this shield matter so much? For a potential subsurface biosphere, it could be everything. Cosmic rays and high-energy particles from distant supernova constantly bombard interstellar space. Without a magnetic field to deflect these particles, they would penetrate deep into the planet's ice shell and into the ocean below. Over geological timescales, this relentless radiation could sterilize the water, breaking apart the complex organic molecules that are the precursors to life. A strong magnetosphere acts as a deflector shield, bending these deadly particles away and safeguarding the delicate chemistry happening in the dark depths. But a magnetic field does more than just protect, it also creates beauty in the absolute darkness. If a rogue planet has managed to retain even an incredibly thin atmosphere, perhaps from volcanic outgassing or a captured wisp of gas, its magnetic field would provide a canvas for the most lonely light show in the universe. Charged particles channeled by magnetic field lines toward the poles would collide with those tenuous atmospheric gases. The result would be planet-wide aurorae. Not just shimmering curtains at the poles, but potentially aurorae that engulf the entire world in a silent, shimmering glow of crimson and emerald. The only light on this frozen surface would not come from a sun, but from the planet's own protective heart dancing in the perpetual night. This transforms our image of these dark worlds once more. They are not merely inert lumps of ice and rock. They can be dynamic, shielded fortresses with internal engines powering both protection and breathtaking, solitary beauty, a testament to the enduring and active nature of worlds we once thought were forever frozen in time. The silent aurorae of a magnetic rogue planet are a testament to its hidden energy, but that energy also translates into motion. The speed of these dark wanderers is not a gentle drift, it is a scar from their violent birth. A rogue planet does not amble through the galaxy, it flees. Typical ejection speeds range from tens to hundreds of kilometers per second. To put that in perspective, our own Earth orbits the Sun at a stately 30 kilometers per second. A rogue planet flung from a chaotic young system might be moving 3 times that fast or even more. At such velocities, crossing the distance from our Sun to its nearest stellar neighbor, Proxima Centauri, would take less than 100,000 years, a mere blink on the cosmic clock. Over billions of years, a planet moving at these speeds can traverse vast stretches of the Milky Way, becoming a true galactic citizen with no home to call its own. But some rogue planets are in an entirely different class of speed. Astronomers have detected a handful of stars, known as hypervelocity stars, rocketing out of the galaxy at over 1,000 kilometers per second, propelled by gravitational interactions with the supermassive black hole at the Milky Way's heart. The same titanic forces could, in theory, launch planets on similar trajectories. Imagine a binary star system, 2 stars orbiting each other, that wanders too close to the galactic center's black hole. The black hole's immense gravity could tear the binary apart, capturing one star and violently flinging the other, and any planets it held, outward at a significant fraction of the speed of light. A planet surviving such an event would become a hypervelocity rogue, a dark bullet shot from the most powerful cannon in the galaxy, destined to leave the Milky Way entirely and sail into the intergalactic void. Its speed would be the ultimate clue to its origin, a fingerprint of the most extreme environment imaginable. For the more common rogue planets, their speed and direction of travel are a cosmic breadcrumb trail. By carefully measuring a rogue planet's proper motion, its tiny shift against the backdrop of far more distant stars, and combining that with an estimate of its distance, astronomers can trace a vector backward through time. This is how we attempt to answer the poignant question of where it came from. Did it originate in a nearby stellar nursery like Orion, or was it ejected from an older, more distant star system now lost in the galactic crowd? The trajectory is a silent story. A rogue planet moving slowly relative to the local stars might be a recent exile still lingering near its birthplace. One moving at a sharp, unusual angle to the galactic plane could be an immigrant from a disrupted dwarf galaxy, a captive from an ancient merger event billions of years ago. Each velocity tells a tale of gravitational chaos, a single day, a point in the galaxy's long and violent history of scattering its children to the wind. The silent trajectories of these galactic nomads trace lines across the void, lines that could, by the purest chance, one day intersect our own. This leads us to a thrilling and slightly unsettling mystery. Could a rogue planet ever visit our solar system? The sheer scale of space makes a direct, close encounter with an inner planet like Earth extraordinarily unlikely, almost to the point of impossibility within the lifetime of our species. But the outer reaches of our celestial home are a different story. The odds improve when we consider the vast domain of our Sun's influence, a sphere of gravitational dominance stretching nearly 2 light-years out to the Oort cloud. This distant shell of icy debris is the solar system's final frontier. Astronomers calculate that a rogue planet, perhaps one the size of Neptune, could pass through this remote region once every few 100 million years. While that is a long time on human scales, it is a regular occurrence in the life of a star. The consequences of such a visit, however, would be anything but quiet. The intruder's gravity would be a stone thrown into a still pond. As it plowed through the sparse but vast Oort cloud, its immense pull would perturb the delicate orbits of countless icy bodies. It would fling some out into interstellar space forever, but it would nudge a great many others inward, sending them on long, falling trajectories toward the sun. The result could be a comet shower, a dramatic increase in the number of these icy visitors plunging into the inner solar system over the subsequent millions of years. Some could be diverted onto collision courses with planets. The rogue planet itself might not come closer than the orbit of Pluto, but its gravitational echo could ripple across the solar system for eons, a signature of its passage written in the altered paths of comets. But what if one came closer? Let us speculate on a truly dramatic scenario. A Neptune-sized dark wanderer, still faintly glowing from internal heat, enters the outer solar system, perhaps venturing as far in as the orbit of Uranus. From Earth, what would we see? First, the astronomers. Their sky surveys would detect a new point of light where none existed before, moving against the fixed stars at an alarming, non-cometary speed. It would not have a tail, but its infrared signature would be intense. As it drew nearer over months and years, it would become a new, steady star in our night sky, visible to the naked eye, slowly marching through and disrupting familiar constellations. Its gravitational influence would become measurable, minutely tugging on the outer gas giants, causing tiny wobbles in their orbits that our deep space probes would radio home. The night sky, a constant tapestry for all of human history, would visibly host a foreign world, a permanent reminder that we are not an isolated island, but part of a dynamic and sometimes unpredictable galactic neighborhood. The very presence of such an object would rewrite our understanding of solar system dynamics in real time, a live experiment in celestial mechanics unfolding before our eyes. A rogue planet's silent journey hints at a deeper cosmic secret. Our 14th mystery connects these lonely worlds to the greatest unsolved puzzle in all of physics, the nature of dark matter. For decades, astronomers have known that galaxies, including our own Milky Way, behave as if they contain far more mass than we can see. Stars orbit the galactic center too quickly, their speed betraying the grip of an immense, invisible gravitational source. We call this missing mass dark matter. It does not emit, reflect, or absorb light, yet its gravitational influence is everywhere. For a time, a fascinating and wild theory emerged. Could this dark matter simply be made of countless dark objects like rogue planets, black holes, or failed stars, drifting unseen in the vast galactic halo? These hypothetical objects were given a name, MACHO, short for massive compact halo objects. The idea was compellingly simple. We already knew rogue planets and brown dwarfs were dark and hard to see. If they existed in truly staggering numbers, their combined gravity could explain the missing mass holding galaxies together. It was an elegant solution, suggesting dark matter wasn't some exotic, unknown particle, but just ordinary matter hiding in the darkest corners of space. To test this, astronomers turned to the same technique we use to find rogue planets today, gravitational microlensing. Throughout the 1990s and early 2000s, large collaborations like the MACHO project and EROS meticulously monitored millions of stars in the Large Magellanic Cloud, a small satellite galaxy of our own. Their logic was straightforward. If the halo of our galaxy was teeming with enough planet-sized or star-sized dark objects to account for all dark matter, then these MACHO would frequently pass in front of stars in the cloud, causing microlensing brightening. They watched for years, cataloging the rare flickers. The results were definitive, and they ruled out the wild theory. the number of microlensing events they detected was far, far too low. Rogue planets and similar compact objects could only make up a tiny fraction of the dark matter halo, perhaps less than 20%. The primary component of dark matter had to be something else, something more pervasive and mysterious, like a sea of yet undetected subatomic particles we call WIMP, or weakly interacting massive particles. So rogue planets are not the dark matter, but this profound null result still tells us something extraordinary. These surveys confirmed that dark, planet-sized objects do exist in the galactic halo, and in numbers that align with our modern estimates of billions or trillions of rogue worlds. They are a form of normal or baryonic dark matter. They are the shadows we can just barely perceive, the known unknowns in a cosmos dominated by a deeper, more profound unknown. This connects the intimate mystery of a single drifting world to the grandest scale of the universe. Every rogue planet we infer is a tiny piece of the visible mass budget, a small, dark stitch in the luminous tapestry of the galaxy, while the true dark matter remains the invisible loom on which that tapestry is woven. That failed search for dark matter still revealed a galaxy filled with dark wanderers, and their collective presence raises a profound possibility. These countless rogue planets are not merely cosmic debris, they could be active architects shaping the very structure of the galaxy as they travel. This is the 15th mystery. Could rogue planets actually trigger the birth of new stars? To understand this, we must visit a stellar nursery, a vast, cold molecular cloud. These clouds are the raw material of stars, but they are often too diffuse and tranquil to collapse on their own. They need a trigger, a gravitational nudge to push a dense pocket over the edge. For eons, astronomers have looked to supernova shock waves or the spiral arms of the galaxy itself as the primary architects of star formation. But what about a rogue planet? Imagine a dark world several times the mass of Jupiter, sailing silently for 1 billion years. Its path finally leads it into the heart of one of these immense, dusty clouds. As it moves through this dense fog, its gravity begins to pull on the surrounding gas and dust. It acts like a plow, gathering material in front of it, creating a wake of compressed, denser gas. In its immediate vicinity, the local density of the cloud increases significantly. If the planet is massive enough and moving at the right speed, this compression could be the final push needed for that pocket of the cloud to begin collapsing under its own gravity. A new protostar, a faint, embryonic sun, could ignite in the rogue planet's wake. The planet would not stop, of course. It would continue its journey, leaving behind a new stellar system it helped create, a cosmic Johnny Appleseed sowing seeds of light in the dark. On a broader scale, a whole population of rogue planets constantly drifting through these clouds could act as a kind of gravitational stir stick. Their combined motions would churn the cloud material, transferring energy, preventing some regions from becoming too quiescent and perhaps even disrupting others. This subtle stirring could influence the overall efficiency of star formation in a galaxy, determining how many stars are born large and bright versus small and dim. It paints a stunning new portrait of these nomads. They are not just orphans or exiles. They are potential catalysts, silent agents of creation whose greatest legacy might be the stars they leave burning behind them in the dark. A captured rogue planet would be more than a new neighbor. It would be an interstellar library. Its very substance is a frozen record, an astrochemical time capsule from a distant solar system we may never otherwise see. Every planet in our own system carries a specific fingerprint, a unique blend of elements and isotopes forged in the heart of our sun and mixed in the protoplanetary disk that birthed us. The ratio of carbon to oxygen, the specific flavors of noble gases like neon and xenon, the abundance of rare earth metals all tell the story of our local cosmic kitchen. A rogue planet, however, was cooked in a different kitchen entirely. Imagine it formed around a star richer in heavy elements than our sun, or perhaps one that was more anemic in carbon. Its rocks and ices would lock in that foreign recipe. If it was ejected early, that record remains pristine, uncontaminated by billions of years of stellar winds or planetary migration. By contrast, planets that stay in their home systems are constantly processed, baked by their star, and bombarded by material from other parts of the disk, blurring the original signature. A rogue planet is a snapshot of the initial conditions from another part of the galaxy. Analyzing its composition would be a monumental task for a future interstellar probe, but the data would be revolutionary. We could finally answer fundamental questions about the diversity of planetary ingredients. Is our solar system's mix of elements typical, or are we an outlier? Do stars with more iron tend to form rockier planets? Does the isotope ratio of nitrogen in another system match ours, or tell a completely different story of galactic chemical evolution? This one dark world, if we could ever get our hands on a piece of it, would provide a comparative data point of priceless value. It would tell us not just about one lost world, but about the entire family of planets that once perhaps circled its forgotten sun. A captured rogue planet is a cosmic archive, but what if the archive itself were the creation of a long-vanished intelligence? This leads us to a mystery that straddles the line between hard science and profound speculation. Could a rogue planet be a starship? For a civilization facing the certain death of their expanding sun, the ultimate act of survival would not be to flee on a metal vessel, but to take their entire world with them. The engineering challenges are so vast they border on the mythological. First, you would need to dismantle your star, a Type II civilization on the Kardashev scale, one capable of harnessing the total energy output of its sun, might construct a Dyson sphere not to live within but to use as an engine. By channeling that star's radiation into a focused jet, perhaps using solar sails the size of continents, you could, over millennia, nudge your planet's orbit further and further outward until it reached escape velocity. The process would be glacially slow, a gentle push across eons. Alternatively, imagine planet-scale fusion drives bored deep into the crust, firing like titanic engines to propel the world on a chosen course. The energy requirements are incomprehensible, but for a society that mastered its sun, perhaps not impossible. Then comes the greater challenge: light and heat. Without a star, your world becomes a frozen tomb. The solution would be an artificial sun, a contained fusion reactor suspended in a stable orbit, providing a day-night cycle and warmth to the biosphere below. This is not merely moving a planet, it is building an entire, miniature, mobile solar system from scratch. The existential weight of such a journey is heavier than any engine. You're committing your entire species, every mountain, every ocean, every city, to a voyage that will last for millions, even billions of years. Generations would be born, live, and die seeing the same constellations outside their artificial sky, watching their destination star grow imperceptibly brighter over millennia. The very concept of home transforms from a place in a galaxy to the world you're riding upon. This nomadic civilization would become its own cosmos, a closed ecological and cultural system sailing the void. They would be the ultimate archivists, carrying not just their history in books, but their entire living history in the soil beneath their feet. The goal would not be a new star to orbit, but perhaps a lush, young planetary system to gently join, or a permanent life as galactic wanderers, observers of the universe from the ultimate slow ship. If such a world exists, it would be the most profound artifact imaginable, a planet that is not a natural creation, but a masterpiece of cosmic engineering, its dark journey a purposeful exile into eternity. The profound silence of these dark worlds extends far beyond their frozen surfaces, into the very nature of any intelligence that might call them home. This brings us to our 18th great mystery, a cosmic radio silence that connects directly to one of astronomy's most famous questions, the Fermi paradox. If the universe is so vast and old, and life is even remotely possible, then where is everybody? Our search for extraterrestrial intelligence, known as SETI, has for decades listened intently to the stars, scanning the heavens for the faint whisper of a radio signal, a deliberate beacon, or the accidental chatter of a technological civilization. But this search assumes a fundamental thing, that intelligent life develops on a planet like Earth, orbiting a sun with a surface exposed to the sky. Rogue planets shatter that assumption. If life exists in a global ocean sealed beneath miles of ice, its entire evolutionary path is funneled into a very different channel. A subsurface civilization on a rogue planet would have no sky. Their entire universe is a pressurized, pitch-black abyss. They would have no concept of stars, no knowledge that a universe beyond their icy ceiling even exists. For them, the idea of building a powerful radio transmitter and pointing it at the void above would be utterly meaningless. Why would they? Their technology would develop to navigate and harness their deep ocean environment, perhaps mastering bioluminescence, sonar, and the geothermal vents that power their world. Their greatest scientific achievements might involve understanding the intricate geology of their planetary shell, not the physics of interstellar space. Even if they somehow deduced the existence of an outside cosmos, punching a signal through miles of solid ice and into the vacuum would be an engineering challenge of staggering proportions with no apparent reward. Their civilization would be inherently inward-looking, a brilliant culture flowering in absolute isolation, completely invisible to our most sensitive radio telescopes. This presents a chilling solution to the Fermi paradox. The galaxy might be teeming with life, but it is life that is forever trapped in dark oceans, unaware of the cosmos and undetectable to our methods. They are not hiding, they are simply living in a universe so different from our own that our paths of discovery may never intersect. The great silence is not a sign of emptiness, but of profound and permanent separation. Colonizing a rogue planet is the ultimate test of human ambition and isolation. The challenges begin with a simple, brutal fact: there is no sun. This means no solar power, no natural day-night cycle, and no external source of warmth. The surface is a frozen wasteland at near absolute zero, bathed in perpetual, star-lit darkness. Any colony could not exist on that surface. It would have to be buried deep within the planet itself, tapping into the only reliable energy source available: geothermal heat. The technology required is staggering. We would need compact, self-sustaining fusion reactors far beyond our current capabilities, or the engineering prowess to drill through miles of ice and rock to harness the planet's internal warmth. Every resource, from air to building materials, would have to be mined and recycled with near-perfect efficiency. The psychological weight would be immense. Generations would live and die never seeing a sunrise, never feeling natural sunlight on their skin. Their entire world would be artificial light, recycled air, and the constant, silent pressure of the ice above. The sky, if they ever visited the surface in a protective suit, would be a static tapestry of stars, unmoving, with no familiar moon or sun to mark the passage of time. Yet the theoretical benefits are profound. A rogue planet offers a stability unknown on any orbiting world. There are no orbital periods, no seasons, no axial tilt to manage. The environment, once mastered, could be perfectly controlled. The resources of an entire world, from its mineral core to its frozen volatiles, would be available for the taking. And it offers the ultimate privacy and security, a hidden fortress drifting unseen in the galactic dark, isolated from the political or environmental turmoil of any star system. Imagine a city not on the ice but within it, vast caverns melted and reinforced, glowing with artificial bioluminescence or fusion-lit parks that mimic a lost Earth. Transportation tubes weave through clear ice tunnels, offering views into dark, subterranean oceans teeming with alien, chemosynthetic life. This civilization would be completely self-contained, a closed loop sailing through eternity. The drive to attempt such a feat would not be for comfort, but for survival, a backup for humanity should our star fail. or a desire to become a truly interstellar species, unshackled from the fate of any sun. It is a dream of ultimate independence written in ice and darkness. The words we choose to describe these worlds shape how we imagine them. This is the namesake enigma, a semantic mystery hiding in plain sight. Astronomers and science writers use a small constellation of terms, each carrying its own subtle weight and story. Rogue planet is the most popular, evoking a sense of lawless rebellion, a cosmic outlaw that broke free from the gravitational order of its star system. It is a dramatic, almost romantic label suggesting agency and defiance. Orphan Planet leans into a different emotional register, one of tragedy and loss. It paints a picture of a world abandoned, cast out from the warmth of its stellar family, evoking a poignant loneliness. Nomad Planet feels more neutral, even noble, implying a purposeful, endless journey across the stellar steppes. Then there are the more clinical terms, free-floating planetary mass object or interstellar planet. These avoid metaphor altogether, sticking to a dry, technical description of an object's state and location. So which is most accurate? The answer depends not on poetry but on origin. If the world formed in isolation from a tiny cloud of gas and dust, it was never part of a stellar family, so calling it an orphan is incorrect. It was always alone. If it was violently ejected from a system, then rogue or orphan both fit the violent history. The problem is when we spot a faint, lonely point of infrared light or catch its microlensing shadow, we rarely know its origin story. We cannot tell if it is a true rebel or a solitary born. This ambiguity is why the International Astronomical Union, the official body responsible for celestial nomenclature, has not settled on a single, formal definition. Their focus is on classifying what we can measure, not the stories we infer. This leads to a wonderfully practical headache. Our solar system has a clear naming convention. Planets are named for Roman gods, moons for figures from mythology, all orbiting a central star we call the Sun. But how do you name billions of objects that have no address, no star to call home? You cannot give each one a unique mythological name. There simply are not enough myths in all human cultures. A systematic approach might involve catalog numbers based on coordinates and discovery date, resulting in names like FLPMO 357, a string of letters and numbers as cold as the space the object drifts through. This lack of a name reinforces their anonymity, their status as statistical entities rather than individual worlds. Yet, for the few we study closely, the human urge to personalize wins out. We get designations like CFB Sir 2149-0403, or the more evocative SIMP J01365565 plus 09334773, often shortened to a nickname like The Accident for a particularly strange brown dwarf that behaves like a planet. This tension between cold data and warm storytelling is at the heart of astronomy. The names we give these dark wanderers, whether drawn from myth or math, are our first attempt to bring them into the human narrative, to transform a silent data point into a character with a story waiting to be told. A distant glint of sunlight on an alien ice field could be hiding in plain sight. While we search the galactic core for microlensing shadows, a far more intimate population of rogue planets might be silently drifting through our own solar neighborhood, close enough to see directly, yet somehow remaining unseen. This is the tantalizing possibility of lens flare anomalies, unexplained flashes of light in our telescopes that have no obvious source. The idea is deceptively simple. If a rogue planet with a highly reflective surface of water ice or methane snow were to pass through the inner solar system, even at a great distance, sunlight could strike it at just the right angle to create a brilliant momentary glint. From our perspective, it would look like a new star winking on for a few seconds or minutes, then vanishing just as quickly. These are not the slow, predictable brightenings of microlensing, but sudden, localized sparkles in the dark. The challenge is that our sky is full of transient phenomena, satellites tumbling, meteors flaring, and cosmic rays hitting camera sensors. Anomalous flashes are often dismissed as noise or space junk. But what if, buried in decades of archival data from observatories or even in the footage of countless amateur astronomers, there exists a pattern of these unexplained glints that trace a slow, moving path across the sky, the signature of a dark, frozen world on a close approach. This connects directly to the long and storied search for Planet X, a hypothetical large planet orbiting far beyond Neptune. For over a century, astronomers have looked for a hidden giant perturbing the orbits of distant icy bodies. But the lens flare anomaly theory flips the script. Perhaps the object we have been looking for is not in a stable orbit at all. Maybe it is a rogue planet, a Neptune-sized wanderer currently passing through the outer solar system. Such an object would be cold and incredibly faint, but not completely dark. If its surface were fresh ice, it could reflect enough sunlight to be detectable by our most sensitive surveys, but only if we were looking in exactly the right place at the right time. Its motion would be unusual, not following a neat elliptical path, but a more linear trajectory against the stars. It is entirely possible that such an object has already been photographed and catalogued as a faint dot in a single image, then dismissed as a background star or a minor asteroid because it never appeared again in that location. The vastness of the sky and the infrequency of our deep scans of any single patch mean a slow-moving object could easily slip through the net. This mystery pulls the grand scale of the galaxy down to a deeply personal level. The greatest dark wanderer we are searching for might not be in the heart of the Milky Way, but right here in our own celestial backyard, a silent, frozen visitor just passing through, its presence hinted at only by a fleeting, forgotten sparkle in an old photographic plate. A single rogue planet could drift for a time longer than the universe's current age. In that near eternity, under conditions of profound isolation, cold, and pressure, the ordinary rules of matter might begin to bend. This speculative leap takes us to the quantum wanderers, where the physics of the impossibly small could, over cosmological timescales, manifest on a planetary scale. It is a realm of pure theory, but it stretches our imagination to the absolute limits of what a world could become. Consider the core of an ancient, massive rogue planet, one that never held a moon and has cooled for tens of billions of years. Under the crushing weight of its own ice and rock, the matter in its heart is compressed to densities that rival the inside of a neutron star. In this environment, protons and neutrons may themselves dissolve into a soup of even more fundamental particles, quarks and gluons. This quark matter could exhibit bizarre quantum properties like superfluidity, where it flows with zero friction, creating a frictionless quantum ocean deep within the planet's center. The entire core could become a single, coherent quantum object on a macroscopic scale. Even more speculative is the potential for quantum tunneling on a grand scale. In the ultra-cold, near-zero temperature environment of the planet's interior, atomic nuclei are packed tightly but separated by barriers of repulsive force. Normally, they could never fuse without immense heat and pressure, but quantum mechanics allows for a tiny, non-zero probability that a particle can simply appear on the other side of a barrier it classically shouldn't cross. Over billions of years in this frozen, pressurized state, could quantum tunneling allow for slow, cold nuclear fusion or transformation of elements, a faint radioactive heartbeat powered not by heat, but by the strange rules of probability itself? The most extreme thought involves the stability of the universe's vacuum. Some theories in particle physics suggest our universe exists in a metastable state, a valley of stability that is not the lowest possible energy level. A catastrophic event like an extremely high-energy collision could theoretically trigger a bubble of true vacuum to form and expand at the speed of light, rewriting the laws of physics as it goes. While the energy required is astronomically beyond anything possible in our particle colliders, the near-absolute zero, high-density environment within a super-cooled rogue planet's core represents a unique and uncharted phase of matter. Could some unforeseen combination of conditions there over eons tip the balance? It is an almost unimaginable scenario where a single dark wanderer could, by virtue of its age and isolation, become a seed for a cosmic reset. This is the true frontier. These ideas are not established science, they are glimpses at the map's edge, where our known physics dissolves into question marks. They remind us that a rogue planet is more than a world without a sun. It is a natural laboratory for conditions we cannot replicate, a silent experiment running on a billion-year clock, testing the universe's most fundamental rules in the dark. That profound isolation is not evenly spread across the galaxy. The silent paths of these dark wanderers trace a map of cosmic history, and where they are found tells us when and how they were cast adrift. Our 23rd mystery asks a fundamental question of location. Are rogue planets concentrated in the Milky Way's bustling disk, or do they swarm in its vast spherical halo? This galactic address is a direct clue to their origin story. The Milky Way is not a flat pancake of stars. Picture it as a fried egg. The yolk is the central bulge, a dense sphere of ancient stars. The white is the thin disk, a relatively flat plane where our sun resides, filled with younger stars, gas and dust. Encasing this entire structure, like a faint, glowing mist, is the stellar halo, a vast, spherical cloud of the galaxy's oldest stars and globular clusters. Now, where do the Nomads live? If a rogue planet is found in the thin disk, it is likely a relatively recent exile. It was born in one of the disk's many stellar nurseries and ejected within the last few billion years, its trajectory still roughly aligned with the plane of galactic rotation. It is a local story, a piece of debris from the ongoing construction in our stellar neighborhood, but a rogue planet residing in the halo tells a tale of unimaginable antiquity. The halo is the galaxy's archaeological site, holding stars and structures that formed over 10 billion years ago, before the disk itself had fully settled. A rogue planet there is a primordial relic. It could have been ejected from one of the first generations of star systems, or even from a small dwarf galaxy that was devoured by the Milky Way in a long-ago merger. Its presence in the halo marks it as a fossil from the cosmic dawn, a dark witness to the galaxy's most violent and formative epochs. Determining which population is larger, disk or halo, would fundamentally reshape our understanding of galactic evolution. A halo dominated by rogue planets would suggest the early universe was a chaotic factory for creating and immediately discarding worlds. A disk-heavy population would indicate planetary ejection is an ongoing, common process in modern, mature star systems like our own. The answer, however, is locked behind a formidable technical wall. The primary tool for finding these worlds, gravitational microlensing, provides a maddeningly incomplete set of clues. When astronomers detect a microlensing event, they measure two key things: the duration of the brightening and the amount of light magnification. From this, they can estimate the mass of the lensing object, the rogue planet. But to place it on the galactic map, they need its distance, and that is incredibly difficult to pin down. The event is a chance alignment between the rogue planet, a distant background star, and Earth. We know the distance to some background stars, but we do not know where along that immense line of sight the rogue planet actually lies. Is it a relatively nearby object in our galactic disk, or a much more distant one in the halo? Resolving this ambiguity often requires a second observation from a telescope in a different location, like the other side of Earth's orbit around the Sun, to provide a stereoscopic view called parallax. This is rarely possible for these fleeting, unpredictable events, so our map of rogue planets is frustratingly flat, a collection of dots without depth. We know they are there, but we cannot always tell if they are in the city streets of the disk or the remote countryside of the halo. Each confirmed location, when it can be determined, is a precious data point. It is like finding a single, specific grain of sand on a beach and knowing whether it came from the nearby cliffs or was carried by an ancient river from mountains far inland. This painstaking work is slowly coloring in our portrait of the dark galaxy, revealing whether we live in a cosmos where planetary exile is a current event or a ghost story from the distant past. Their galactic journey is measured in trillions of years, a timescale that makes the age of our universe seem like a single breath. So we must ask, how does a cosmic nomad finally meet its end? The most common fate is not a dramatic collision, but a slow, silent fade into the cold. A rogue planet has no external source of heat. Over eons, its internal warmth, whether from radioactive decay or the lingering fires of formation, steadily leaks away into the vacuum. It cools degree by imperceptible degree over hundreds of billions of years. Eventually, its temperature drops until it matches the faint, pervasive glow of the cosmic microwave background, the leftover radiation from the Big Bang itself. At that point, it becomes a perfect thermal equilibrium with the universe, a dark, cold stone indistinguishable from the empty space around it. It is a death by degrees, a fading of its last whisper of infrared light into the eternal night. But the cosmos offers more violent conclusions. A rogue planet on a random path across the galaxy faces a statistical inevitability. Given enough time, its trajectory could intersect with another star system. A direct impact with a star is the most final end, the dark world plunging into the stellar furnace and being vaporized in an instant, its atoms scattered and recycled into the star's plasma. A near miss could be just as destructive. Passing too close to a star or a massive planet like Jupiter would subject the rogue to immense tidal forces. These forces could stretch and compress it, heating its interior to melting points and triggering global volcanic cataclysms. If the encounter is extremely close, the tidal pull can become stronger than the planet's own gravity holding it together. The world would be literally ripped apart, shredded into a stream of molten debris that spirals into the star or forms a new, temporary ring system around the giant planet that destroyed it. It is a death by celestial gravity, torn asunder by a force it could not escape. Then there is the ultimate gravitational predator. A rogue planet wandering near the supermassive black hole at the center of the Milky Way would face a bizarre and terrifying fate. It would not simply fall in. As it approaches the event horizon, the difference in gravitational pull between the side facing the black hole and the side facing away becomes so extreme that the planet is stretched into a long, thin strand of material, a process called spaghettification. This noodle of planetary matter would then spiral into the black hole's accretion disk, adding a tiny increment of mass to the behemoth, its unique chemical signature lost forever in the chaos. In the unimaginably distant future, when all stars have burned out and galaxies have evaporated, these dark wanderers might inherit the cosmos. They will be among the last macroscopic objects adrift in a universe grown cold and dark, their journeys continuing long after the lights have gone out. This final mystery adds a layer of profound, almost melancholic scale to their story. They are born in violence, they live in silent isolation, and their ends span the spectrum from the quietest fade to the most violent dissolution, their stories written across the lifespan of the universe itself. The final and perhaps most hopeful mystery lies not in the dark past of these worlds, but in the brilliant future of our ability to see them. Our hunt is on the cusp of a revolution, powered by two extraordinary observatories that will turn whispers into shouts. The James Webb Space Telescope is already rewriting the rules. Its unparalleled infrared vision acts as a heat-sensitive camera for the cosmos, allowing it to directly image rogue planets in their stellar nursery infancy. While earlier telescopes might have glimpsed a faint smudge, Webb sees in stunning detail, analyzing the chemical composition of their atmospheres, if any remain, and measuring their faint glow to determine age and mass. It is transforming candidate objects into studied subjects, giving us our first true portraits of these young exiles while they still retain the warmth of their violent birth. But to truly understand the scale of the dark galaxy, we need more than detailed portraits of a few young wanderers. We need a census. That monumental task falls to the Nancy Grace Roman Space Telescope, set to launch later this decade. Roman is not just another telescope, it is a statistical engine designed for discovery. It will perform the largest, most sensitive microlensing survey ever conceived, staring at the same dense star fields toward the galactic bulge for months at a time. Where current surveys catch rogue planets by lucky, fleeting alignment, Roman will watch with relentless patience, catching thousands of these events. It will see not just the Jupiter-sized giants, but has the potential to detect rogue worlds as small as Mars, finally piercing the veil that has hidden the smaller, more numerous population from our view. The data Roman returns will be transformative. For the first time, we will move from intriguing estimates to a clear statistical picture. We will have a robust answer to the question of how many billions or trillions of these nomads truly drift through the Milky Way. We will begin to map their distribution, understanding if they cluster in the disk or swarm in the halo. Each microlensing event, with Roman's precision, will provide better clues to the rogue planet's mass and distance, slowly building a three-dimensional map of this dark population. This is the key to unlocking almost every mystery we have explored. A reliable census tells us about the violence of planetary system formation, the frequency of ejections, and the true architectural blueprint of our galaxy. It guides our search for the most ancient wanderers and refines our models for where life might cling on in the dark. The silent, endless night is about to get very, very crowded with data. The next chapter in the story of rogue planets will not be written by theorists alone, but by the light of these new eyes in the sky, finally revealing the true shape of the darkness. From the violent chaos of their birth to the silent eternity of their fate, these dark wanderers force us to rewrite the cosmic rulebook. Rogue planets are more than astronomical curiosities. They are a fundamental challenge to our most basic definitions. What is a planet if it does not orbit a star? What is a home if it is a warm ocean sealed under miles of ice in perpetual night? What is a solar system if the most common worlds sail alone through the spaces between the stars? For centuries, we envisioned the galaxy as a collection of orderly families, each world circling its sun. Now we must accept a far stranger and more magnificent reality. The silent, dark nomads may well be the true majority, the most common form of planetary existence in the Milky Way. Our own sunny neighborhood, with its familiar orbits and predictable seasons, might be the galactic exception, not the rule. This journey through 25 mysteries reveals a cosmos far richer and more mysterious than we ever dreamed. It is a universe where worlds can be born alone, live in darkness, and travel for eternity. It is a place where life, against all odds, might find a way in the deepest, blackest oceans, and where the very fabric of matter might be tested in the heart of a frozen, ancient wanderer. As you look up at the starry sky tonight, remember this: for every point of light you see, there may be a dozen dark companions drifting unseen, a silent procession of lonely travelers on journeys that began before our sun ignited and will continue long after it fades. Our place in this cosmos is both humbling and exhilarating, a single bright point in a sea of magnificent darkness. Which of these 25 mysteries captured your imagination the most? Was it the possibility of life in an eternal abyss, the chance a dark world could one day pass through our own solar system, or the staggering idea that they might outnumber all the stars? Let us know in the comments below and subscribe to join us as we continue to explore the deepest wonders of space.